We've all been there, right? You're mindlessly copying code. You paste it into a chatbot, and you get an error.
Yeah, the classic copy-paste loop.
Exactly. Then you just paste that error right back. It's an exhausting, endless loop. Bead. But what if you could just, bypass that completely?
Right.
Imagine an AI agent living directly inside your terminal. It's working those loops for you entirely for free.
It really is a completely different way to build software.
Welcome to the Deep Dive. We're unpacking a highly practical guide today. We're looking at optimizing Claude Code with local LLM workflows. And the mission here is pretty simple. We want to understand how to bridge a powerful cloud AI with your local machine.
Right, because we are moving away from chatty AI assistants. We're stepping into the world of actual agentic coding.
We're going to explore the exact tech stack you need. We'll benchmark small versus large local models.
Yeah, that part is fascinating.
And finally, we'll build a handoff strategy. This strategy saves your API tokens without sacrificing any coding quality.
It's just a profound shift in how developers actually operate.
But before we can build this workflow, we really need context. We have to understand how this new paradigm actually operates. It differs greatly from a standard web chatbot. So let's identify the tools we're stacking together.
Well, Claude Code is fundamentally different from a web interface. It acts actively inside the terminal. It's not just, answering questions.
And for those newer to the workflow, the terminal is just the text-based command screen developers use.
Exactly. So Claude Code reads your project files directly. It creates new files autonomously. It actually runs terminal commands. It doesn't sit around waiting for you to paste prompts.
So we're looking at three main pillars for this local tech stack. First, we obviously have Claude Code itself. That's the dedicated worker living inside your terminal.
Second, we have the local model itself. The source guide uses a model called Gemma.
Right.
But you really can use any local LLM you want.
An LLM is just the core AI system processing the text.
Yep.
Gemma basically acts as the brain running on your machine. You can choose a few different sizes.
They usually range from, 7 billion to much larger parameter counts.
Right, exactly.
And parameters are just the internal connections defining an AI's overall size.
Yeah.
A 7 billion parameter model is fairly lightweight. A 26 billion parameter model is significantly heavier on your hardware.
And then the third pillar is something called LM Studio. This is the crucial bridge in the whole setup.
Okay.
It runs directly on your local computer.
It essentially exposes the model via an API endpoint. An API endpoint is a digital doorway for sharing data.
Specifically, LM Studio creates an OpenAI-compatible endpoint. It usually sits quietly at http://localhost.1234v1.
That local endpoint is absolutely vital here. It's the exact doorway Claude Code actually connects to.
Right.
2-sec silence.
I kind of think of this stack like a physical office setup.
Oh, how so?
It's literally like hiring a junior developer. They sit right at your desk looking at your screen. They aren't in some cloud office across the country.
That's a really perfect way to visualize it. They're completely local, they're fast, and they're looking directly at your local file system.
But exactly, why is LM Studio the required middleman here?
Yeah.
Like, why can't Claude Code just talk to Gemma directly?
Well, Claude Code naturally tries to contact Anthropic's specific cloud servers. LM Studio essentially intercepts that outbound connection.
Yeah. Okay.
It hosts the local model, but speaks the exact language the cloud expects.
So it translates local hardware into an API Claude already understands.
Precisely. It makes the connection totally seamless.
Now that we understand those three pillars, we need to move forward. How do we actually wire them all together?
Right, the fun part.
Claude has to stop talking to the expensive Anthropic servers. It needs to start talking to our local machine instead.
We have to start with the basic terminal setup. You install the Claude Code package first. You must ensure your system can actually find the neatly installed command.
And if it fails, you usually just refresh your shell path. Or you can simply restart the terminal application entirely.
Next, you open up the LM Studio application. You search the interface for the Gemma model. You download those specific model files directly to your machine.
The source material strongly suggests starting with a smaller model first. It's much easier to run on a standard laptop.
Yeah, you can confirm the whole setup works without crashing your computer.
Then you navigate to the local server section in LM Studio. You manually start the API server.
As you mentioned earlier, it usually runs on port 1234.
Now we have to configure the environment variables in the terminal. You export a variable called Anthropic base URL. You point it directly to http://localhost.1234v1.
You also need to configure an attribution header. This is a genuinely crucial insight for smooth performance.
Okay, what is it?
You must explicitly set Claude Code attribution header to 0.
Let's pause on that for a second. Why is that specific header so incredibly important?
It comes down to how local AI memory works. Extra headers changing between requests force the model to reset.
Oh, I see.
It essentially dumps its short-term memory and reevaluates the whole prompt.
Oh, that makes total sense. Setting it to 0 keeps the memory cache intact.
Exactly.
Keeps everything running smoothly. Beat. But I noticed a really weird quirk in the guide here.
Yeah.
We also have to set an Anthropic token. And we use a random dummy key like the word Ilm Studio.
Mm-hmm.
Why do we need a secure key if the model runs completely locally?
It's really just an architectural leftover in the code. Claude's underlying architecture is heavily hardwired to expect a secure key.
Oh, wow.
Even a totally fake key satisfies the system's strict security requirement.
That's actually fascinating. The software blindly demands a key, so we just give it a shadow.
Give it a shadow, exactly.
Once that's done, you finally launch Claude Code. You just specify your local model's exact name.
But you must be incredibly careful about where you run it.
Right. So how do we actually prevent this autonomous AI from accidentally destroying important project files?
You should always launch it inside a dedicated, isolated test folder. You explicitly restrict its file access to just that current directory.
All right, always launch it in a test folder and restrict file access.
Exactly. You want to prioritize safety first.
So the wiring is now fully complete. The local server is humming along on the machine.
Yep.
But the real practical question still remains. Does a totally free local model actually write decent code?
Let's look at the actual benchmarks. The guide's author tested a basic HTML to-do list page. It was a very simple, clean, and isolated test.
They started the test with the 7 billion parameter Gemma model. It surprisingly handled the initial UI generation almost perfectly.
It quickly created the basic structural page. The resulting layout looked perfectly fine in the web browser.
Small models are generally very fast to respond.
They are remarkably good for generating simple first drafts.
But then a major weakness suddenly appeared. The author asked the AI to add real interactive behavior.
Right. They wanted the input field to actually add new tasks.
The model seemingly finished the coding task very quickly.
Yeah.
But absolutely nothing happened when clicking in the browser.
The developer console just showed a glaring red structural error.
The author naturally sent that error back to the terminal. They asked the local model to just fix it.
And the 7 billion parameter model completely fumbled the debugging process.
Yeah.
It missed the actual root cause entirely. The HTML structure had broken or totally missing div tags.
And the model blindly tried changing JavaScript logic instead. Just kept repeating the exact same logical mistake.
Over and over.
I have to admit, I still wrestle with trusting local models myself.
Oh, yeah.
Beat. There's truly nothing more frustrating than watching an AI confidently fix the exact wrong line of code over and over again.
Yeah, it's a very common pain point right now. Small models simply lack the cognitive depth to hold complex logic trees. They lose the broader context of how the files connect.
The author then switched strategies to a 26 billion parameter model. They had run it on a much stronger desktop machine.
It was noticeably slower to generate the initial text. It requires significantly more RAM and dedicated VRAM to function.
VRAM is just dedicated memory on your graphics card for complex calculations.
Right, but the final output quality was vastly superior. It handled real feature work almost effortlessly.
It actually understood the underlying UI logic.
Exactly. It could successfully debug its own structural mistakes. Parameter size truly matters when you get into complex routing.
Where exactly is the tipping point between a model being genuinely helpful and a model just being a liability?
Well, small models excel at generating basic templates and simple text. They fail completely when deep logical correction is required.
Right.
Large models maintain the broader architectural context much better.
Basically, small models build drafts. Large models actually solve the logic.
That's the perfect way to summarize it.
If small models make constant mistakes, we face a real challenge. If large models completely tax our hardware, we cannot run everything locally.
No, we desperately need a cohesive strategy. We must actively balance local models with paid cloud AI.
The source text introduces the handoff philosophy here. It's a really brilliant way to manage your computational resources.
Paid models like Claude or Gemini act as the brain. You specifically use them for hard project planning. They handle the deep reasoning and the core system architecture.
Local models like Gemma act as the repetitive muscle. You use them for the highly clear, repetitive coding tasks.
They create the basic HTML framework pages. They write the endless unit tests.
Right. They add the necessary documentation comments.
The brain creates the overarching master plan. The muscle blindly executes the mechanical, repetitive steps.
This specific workflow reveals something absolutely amazing about Claude Code. It doesn't work anything like a normal chat window.
Whoa! Just think about what it's actually doing in the background. It reads files, decides on changes, edits code, checks the terminal result, and fixes obvious errors entirely on its own in a continuous loop.
It's truly remarkable to watch it work. The author shared a fascinating timing benchmark.
Yeah.
A relatively simple prompt took 2 full minutes and 41 seconds.
That seems incredibly slow until you realize what actually happened. It wasn't just slowly waiting to type text. It was furiously running an iterative, autonomous coding loop.
It was working completely autonomously in the background. But this iterative loop pushes your local hardware incredibly hard.
The CPU, the GPU, and the system RAM all spiked dramatically during this process.
The author highly recommends using terminal hardware monitoring tools. Something like HTOP helps you closely watch the system load.
You really need to see exactly how hard the machine is working.
How does a developer know exactly when to switch from using the brain to using the muscle?
You carefully evaluate the specific task at hand. If it requires architectural judgment, you definitely use the cloud. If it's purely mechanical execution, you stay totally local.
Use paid AI for judgment calls and local AI for pure execution.
That balance is what makes the whole workflow highly practical.
Sponsor.
It sounds like a beautifully efficient system when it works, but what happens when the local muscle starts failing?
Or when that iterative loop breaks down entirely.
You have to troubleshoot the system very carefully. Basic network connection issues are surprisingly the most common pitfall.
Let's say you run the heavy model on a stronger desktop across the room. You're just typing commands on your lightweight laptop. Typing localhost won't work anymore.
Right. You must use the actual local IP address of that specific desktop.
Okay.
It might look something like 192.168.150 on your network.
You just update the Anthropic base URL with that exact IP address, but then there are the complex behavioral issues to actively manage.
The author gives a very strict, non-negotiable rule here. Do not constantly fight a weak local model.
If a 7 billion parameter model fails twice on the exact same bug, you stop. You must stop the autonomous loop immediately.
You step in as the human. You manually fix the broken HTML structure yourself.
Right.
Then you simply let the local model continue its work.
This really leans into the overarching philosophy of the entire guide. This local setup is definitely not an autopilot system. You are still the primary software developer.
The AI is purely just an interactive assistant. It constantly needs your structural guidance.
You must test the code incredibly often. You must review almost every single change before blindly trusting it.
And you must actively monitor your hardware limitations constantly.
What usually ends up being the ultimate bottleneck in this local setup is it the AI's complex logic or the physical hardware?
Well, the continuous iterative looping exhausts memory and processing power extremely rapidly. The physical machine usually starts to struggle first.
So hardware chokes first, which is why dual machine setups save the day.
Yes. Offloading the heavy model to a desktop frees the laptop entirely.
Let's step back and synthesize this entire journey. We've covered a massive amount of technical ground today.
The future of the developer terminal is rapidly shifting. It's not going to be exclusively cloud-based anymore.
But it's definitely not going to be purely local either. It's evolving into a true dynamic hybrid workflow.
Using the cloud brain for complex architecture fundamentally saves money. Using the local muscle for basic grunt work bypasses annoying rate limits.
It fundamentally changes how we actually interact with large code bases. It gives you a reliable backup when those paid models are totally unavailable.
It also allows you significantly more freedom to test and repeat rapidly.
And it ultimately brings us to a critical realization about project control. Keeping your raw code on a local machine gives you total privacy. You can control your personal side projects entirely. You can fiercely protect sensitive client work from public cloud servers.
Total privacy suddenly becomes a very tangible asset in this specific workflow.
Which leaves us with a genuinely provocative thought to consider. 2 sec silence. If local private AI models rapidly become the undisputed standard for all our daily coding grunt work, how will that fundamentally change our willingness to hand over our most brilliant proprietary ideas to the cloud algorithms?
It's a huge question.
When exactly does data privacy stop being a luxury feature and start being the absolute baseline.
It's a profound question every single developer will face very soon.
Thank you so much for joining us on this deep dive. Keep building, keep questioning the tools, and we'll see you next time. OUTRO Music.